following slides, you'll see that how your level of significance or your confidence level affects the decision, affects the number. Okay, standard normal distribution. Now, what is a standard normal distribution? In our last class, we studied normal distribution, which is something if you collect the data, you plot the frequencies, you do the distributions, then you see a bell-shaped curve, a Gaussian curve. That is called normal distribution. Now, the equation, I didn't show you the equation. However, the equation for normal distribution is very goofy, and it's kind of difficult, not difficult, but it's complicated. So if you want to find out any value of x inside that curve, and a function of x inside that curve, to put the bounds or to put the limits on that equation is difficult, is complicated. So what did scientists do? What did they do is they normalized the distribution, which means that what they did is they said that if a normal distribution has a mean 0 and a standard deviation of 1. So they converted all any normal distribution we have to a standard distribution. Now the standard normal distribution has mean 0 and the standard deviation of 1. And this is how we denote the standard normal distribution, that Z is equal to normal with mean 0 and variance 1. Now, if I say variance or standard deviation is interchangeable because 1 or the square root of 1 will be 1 as well. So, if we have a normal function, a function which is normally distributed, or x which is normally distributed, any variable x, which is normally distributed with mean mu and variance sigma square, can be converted to an equal value of z, or can be converted to a normal distribution with using this equation, where z is the statistics for normal standard distribution, x is the mean, that any arbitrary mean that you have selected, mu is the population mean or mean from your sample, and this is the standard error of sampling distribution. So the standard error that we talked about just few slides back, or that we discussed last time. So this is Z is the standard normal distribution. And here you see this is a graph, or this is a sampling distribution, a normal distribution of the speed data that was collected at some place. That this distribution has a mean 5 and a variance 65. When it's converted to a normal distribution graph, this is what you see here. When it's converted to a standard normal distribution, then it has a mean 0 and it has a variance of 10. So we always, to standardize our discussion, to make the things more clearer and easier to understand and to standardize them, we always convert normal distributions to the standard normal distribution because they are easier to interpret. Now one more thing, this curve, it has a mean 0 and the area under this curve is always 1. So the total area of the curve is always 1. And then standard normal distribution. Okay. So why the reason I discussed this standard normal distribution is that because now onwards we won't talk about normal distributions, rather we'll talk about normal distributions, how everything is associated with it, how the curves, how the tables that are the values that are calculated, they are all based on standard normal distributions. So hypothesis testing for large sample. Now, if I have a large sample and I formulate some hypothesis, if I formulate a problem, and then I want to check it, I want to check my data, I want to check my hypothesis against the data that I have collected, then depending upon the sample size, I would either do the z-test or I do the t-test. So for large samples, we do z-test or standard normal test. When we say large sample size, a large data, it's usually something which is greater than 30. Then it's called a larger sample size. And the reason being that if you have like data points which are greater than 30, and when you plot that distribution, that it approximately follows a normal distribution. So for a data size greater than 30 points, we say that we are doing hypothesis test for a large sample size. For a large sample, now in z-test and even in t-test, we do one-tail or two-tail tests. Now, what is one-tail test? See, you are now familiar with this standard normal curve. See, this is a standard normal curve. And this is the critical region. The red one is the critical region. This is the one tail, or it has just tail on either here, or it has a tail either here. So if the z value that you have computed, it falls within this critical region, then you reject your hypothesis. So one tail test looks for a definite increase or decrease in the parameter. So for example, your hypothesis is that the test score of a certain class of your let's say test score of your environment class is 65. That is your based on your past observations, based on whatever your study efforts are, etc. That is what your observation is. That is what your hypothesis is. So you say that the test score for all the class is, the mean value is, let's say, 75. Then you collect the sample from the grades of the few of the students, and you find out the mean, and you compute z value. So your null hypothesis is that the mean grade is 75, and your alternative hypothesis is that the mean grade is less than 75. So you are against your null hypothesis, your alternative hypothesis is in the decreasing, in a definitive decreasing order. Then we conduct one-tail test. Or if your null hypothesis is that the average grade of the environmental engineering class is 75, and your alternative hypothesis is that the average grade of the students in the environmental engineering class is greater than 75, then you are doing a definite increase. In such case, we conduct a one-tail z-test. And this is the critical region. In case of a negative value, here will be the critical region in case of positive value. However, in both cases, whenever your z value that you have computed using the equation that we discussed in one slide before this, if it falls within critical region, then you reject your hypothesis in favor of your alternative hypothesis. So it is the repetition of what I just discussed. If our calculated value lies within the red region, we reject the null hypothesis in favor of the alternative hypothesis. Now examples. Now we'll do few examples so that you'll better understand. This is an example that I selected from a book, and it says that according to an article in a magazine, the workforce average age is decreasing. Now, there was some finance company, what it did is that it read an article that said that the average age of the workforce in a certain town or in a certain country is decreasing. So whatever it used to be, it is not. More younger people are drawn into the workforce. So a finance company wants to find out whether its shareholders' age is also decreasing, because people who work, they buy some shares. So based on this article, this finance company wants to find out if the shareholders' age is also decreasing. And a survey conducted a few years ago showed that the company's shareholder average age is 55. So this is what 55 is based on the past data set that the company had collected. So then the null hypothesis, their null assumption or the null hypothesis or the basic assumption, they are saying that no, the mean average age of the population is of the workforce is greater than 55. That is what they are assuming. That is what they want to see, whether the the mean age is greater than 55. That is what their assumption is. Because they do not totally agree with what they read in this article, so their assumption is that mu is greater than 55. Now, the alternative hypothesis, the opposite hypothesis is that mu is less than 55. The mean age of the workforce is less than 55. Their basic formulation, their statement is that the mean age of the workforce is greater than 55. The alternative is mu is less than 55. Now, to see whether their claim or whether their thought or whether their hypothesis is correct or not, they collect data. So what they did is a sample of 250 people was drawn from the shareholders list. They randomly selected 250 people from the shareholders list, contacted them and asked them for their age. So what they found out is on this recent data collection is that the mean age of the shareholders was 53 years and the standard deviation was 12 years of these 250 data points. And they selected the confidence level of 90%. They say that we are 90% confident about our claim that the average age of the workforce is greater than 55. Or, in other words, they allow the significance, or they consider a significance level or alpha of 10% or 0.1, which means they are allowing 10% error in their decision. They are allowing 10% type 1 error. So here is this is the computation for standard error, and the standard error is equal to the standard deviation divided by square root of sample size. So 12 is the standard deviation divided by 250 under root, it gives 0.76. Then z is equal to x, which is based on the data that they collected, minus 50 mu, the mean value that they assumed, which is based on the hypothesis. So 53 minus 55 divided by 0.76 is minus 2.63. Now this is the z value which is computed. For a 90% confidence level or a 10% significance level, now where does this value come from? Now these are the standard values which are computed based on all the curves and the graphs that we have, the normal distribution curve. If you refer to any statistics book, you will find a z table and a t table there. Those z tables give you the standard values of z based on a certain confidence level, or standard values of t based on certain confidence level and the degree of freedom. We'll discuss that later, but let me show you those tables here. Just a second. Okay, and I'll share that with you. Okay. So this is the standard normal cumulative probability table. These are the z values and these are the probabilities. This is for one tail and any negative values. And then similarly, this is for the positive z value, because the positive z area critical region is here. So the value that we computed here is minus 2 point something, and then our confidence level is 90%, which means we are allowing 90%. We are 90% confident about our data. So we remaining in this, we'll select a z value based on that 95% probability. So 0.9 is somewhere over here. We select like based on 0.093